Okay, in this video, we're going to pick up where we left off, right? We talked in the previous video about the basics of paracellular transport, transcellular transport, primary, secondary active transport, all that kind of like the basics of how the nephron is like moving things back and forth. And now we want to talk a little bit more specifically about regions of the nephron and what they're doing. And so here we're starting with up here at the top, right? We're going to start with the PCT. Now, what I'm about to say in this PCT, number one, it's covered in another video about the basics of reabsorption and secretion, which I will post. But the other thing is that even though the PCT does all of these things, other nephron segments do several of them, or at least some of these steps of nephron transport also would occur in other regions. So there's a generalized sort of idea here, but again, if we look at this slide specifically, then we're talking just about the PCT. Okay, so right, we've got and so what this is it's a stepwise progression of what the PCT does. And maybe I should summarize, first of all, what the PCT does overall, right? And overall, it reabsorbs 100% of nutrients. Sorry about that, a little sloppy, right? It reabsorbs 65 to 75% of the water and electrolytes. I just said ions, I guess, huh? Right? And then it does some secretion of largely H+, but other wastes as well, but in, sort of depending upon what's present in the bloodstream as far as a metabolic organic acid waste. As well as things that are exogenous, like medicines or chemicals that come in with our food, things like that. Those would be secreted. Okay, but in a stepwise, okay, and everybody's familiar with this picture, right? We got the nephron wall here. We've got the tubular fluid that's up here, right? That's the inside of the nephron. That's what's going to become urine. We've got our interstitial space. So this is the ISF out here, right? Which is what the nephron is exchanging with, right? And then, of course, the peritubular capillaries down here at the bottom, which would be moving things via both diffusion and bulk flux, as you've seen before. Right? And we can already see that our bulk flux in the peritubular capillaries is going to be set up to be entirely reabsorption. Right? They do not filter. And we'll address this in an upcoming slide, right, to see a little bit more detail on that. Okay, but so here we go. So what's step one of what a PCT does? Now, first of all, these steps, even though I'm going to give them to you sequentially, actually are all occurring at the same time, right? But if we approach them sequentially, we can see how it's like logical dominoes falling, right? But once once we've got it, we've gone through that sequence, make sure that you keep in mind that they all run continuously, right? And so in step one, down here, right, we've got sodium potassium pump. We have primary active transport, right? So let's write in our ATP here, coming in as our energy source. And we're going to generate our sodium gradient, right? And that sodium gradient is, right, so high, low, right, low sodium, and then high, right? Because remember, the filtered low to sodium matches the extracellular fluid, like the same as out here. Right? And so that's step one, is we generate that sodium gradient. Well, because of that, sodium will then diffuse into the cell across a variety of pathways. ENaC would be one, which would, I've got this sort of black dot, now it's red, right? Dot here that serves to represent the carrier of some sort. That could be a channel, carrier or channel. It could be a co-transporter or a counter-transporter. In other words, it could be moving something else. Right? In other words, we're using the sodium gradient for secondary active transport, but we're going to then have a complete pathway for sodium flux to occur into the cell from the tubular fluid, right? We're starting to save some of our filtered sodium here, right, across the cell and then out of the cell over here. And then, of course, we can visualize it being reabsorbed into the nephron. Okay, what does that do? Well, that reabsorbs a lot of cations, right? Because it's the predominant cation in the extracellular fluid that was filtered. So what happens in response to this disappearing is this, right? In other words, we end up with a lot of negative charges left behind. And so we get charge repulsion. That would be step 3, charge repulsion of anions. And there's not one anion, right? There's a multitude of them, right? Our major ones here, chloride and bicarbonate, would end up being passively reabsorbed simply because we reabsorbed the sodium. Okay, so now those guys are being reabsorbed. Now what happens? Well, we're moving a lot of solute, right? Sodium and then these anions, right? Into the interstitial fluid. Yeah, they're being taken up over here. But what's going to happen is as we move these across, we're going to drive, number 4 here, we're going to drive osmotic water removal from the nephron, right? So here's our water that we filtered, and it can travel either paracellularly across the tight junctions here or transcellularly, right, through the cells, right? You know what these guys are, right? So that's an aquaporin, right? Both of them. Now aquaporin 2, you'll hear about later. That's only out in the late nephron. There's a variety of aquaporin versions, but aquaporins in general to get us across the cell. And so we're going to osmotically reabsorb water. Okay, now what happens? Well, now what's left behind, the solutes left behind, become more and more concentrated in this reduced water volume that you're reabsorbing here, right? And so we end up with, right, our remaining solutes becoming concentrated and also becoming reabsorbed. And that's everything that's there, but some of the things that haven't moved significantly yet would be things like potassium and urea, and there's a variety of others, calcium ions. And so those guys would be reabsorbed, right? And then, of course, here they go, right? And so again, look over here on our top right, right? We've got reabsorption of very large portion of the water and electrolytes that we filtered, right? 2/3 of what we filtered at the glomerulus get reabsorbed immediately at the PCT. 2/3 of the electrolytes and water. The nutrients we do even better with, right? 100%. Remember our sodium. We can put our sodium over here, right? Coming in. But instead of it being a channel, we could have it be a co-transporter moving glucose. All right, and then of course we'd need another mechanism of getting it out over here, usually a uniporter, right? And then, right, and so that's very effective at reabsorbing all of the nutrients from this, the filtered load, right? What's in the PCT tubular fluid. Okay, so that's what's happening at the PCT. And again, other elements of this are true in other segments of the nephron as well. And so the logic will, be similarly applied. Right, so let's look at what happens to the concentration of things as we move through this PCT. Right, this is just the PCT down here. This is the length of it. Right, and you can see that. So what we have over here is on our y-axis is the ratio of the tubular fluid to the plasma concentration. So it's sort of like, is it being reabsorbed 1-to-1 with water, or is it, are we doing better or worse with it, right? And so you'll notice that the tubular fluid concentration goes up from 1 for things we want to get rid of, right? Creatinine is a waste. Urea is a waste. The sodium and chloride, the chloride's even, just a hair above, right? Remember, it's okay to have some of these, and chloride sort of lagging the sodium, right? The sodium was our primary, the sodium was actively reabsorbed, whereas the chloride was more passively reabsorbed. So it's not surprising that it lags it a little bit here, right? But it's very close to 1-to-1 in terms of its reabsorption, concentration, I should say. Because remember, water is going with these 2 ions and any other ions that we're reabsorbing, right? Or solutes we're reabsorbing. Okay? If we look at things like bicarbonate, right? Look at that. Now, what does that mean, right? Well, that means that the tubular fluid concentration for bicarbonate falls to less than 1:1, meaning we're being more effective at reabsorbing bicarbonate, right? So most of the electrolytes are going to be right in here, but some of them, bicarb specifically, we're going to be even better at reabsorbing. And we should think of bicarb as being really essential to our acid-base regulation, right? It's a really important extracellular buffer. And so being effective at reabsorbing it is very important. If you go even lower here, right? Now notice, not quite to 0, but these are really small numbers down here, right? We get our nutrients, right? And so the tubular fluid concentration is falling dramatically, reducing our ratio of tubular fluid to plasma, right? And so these guys are going to be very low, and we get close to 100%, maybe not quite, but close to 100% reabsorbed, right, for the nutrients, filtered nutrients. Okay, well, we had previously spoken about how GFR is regulated, right? There's this balance between, we call it tubuloglomerular feedback, right? Where the nephron tells the glomerulus that it's filtering too much or too little, right? The macula densa feedback, right? Well, in addition, it's sort of like not the opposite, but in coordination with that, if you will, there is this thing called glomerular tubular balance. And what that means is that, okay, yes, if GFR goes up, we want to auto-regulate it and hormonally regulate it so that it doesn't go up, right? Or at least not dramatically, right? Because GFR is so big, we need to maintain it at a reasonably steady level. But if GFR is to go up, and yes, we're going to fix that problem, but if it does go up, we also want the nephron to respond by reabsorbing more or less, right, to sort of match the GFR. That's this glomerular tubular balance. It's the degree of filtration telling the nephron what it should do, right? And there's actually a couple of mechanisms of this. The primary one that's sort of well accepted at this point is a mechanotransducer. That's this word up here, right? And it's in the PCT, which makes sense because it's very early, right? So in other words, right after you filter, you want to measure how much you filtered, right? So you can adjust what, and again, the PCT is doing most of the reabsorption, right? Remember, 65, 70%. So we want the PCT to be able to respond. So the PCT has this mechanotransducer. What that means is that it mechanically converts flow, right? It's converting the mechanical action of flow, actually what's called shear stress, on the walls into altered reabsorption, right? And so the actual mechanism, or the actual structures of this mechanotransducer are this thing called a primary cilium, right? That's one. There are also microvilli, and they're important to increase the surface area, but they're also part of this mechanotransducer. And then there's this layer of extracellular attached proteins called the glycocalyx. So all of that is sort of like fuzzy cell projections sticking into the lumen here. And when our flow rate is high, right? We've got our flow, moving along here. So if GFR goes up, we would bend these structures more, right? All these things would be pulled on by what's called that shear stress, the pulling of the fluid against the surface of the wall of the nephron here, right? And we just have these sort of bells and whistles stuck on the inside to more accurately sense that flow rate. So what we do though is when let's say GFR goes up, that would mean that PCT flow would go up. Well, what we need to do then is reabsorb more, right? If you filter more, you want to reabsorb more to match them, right? Glomerular tubular balance, matching them too. And so that mechanotransduction, that conversion of the enhanced flow into action occurs over here. And it's largely revolves around one transporter. It's the NHE3, which is a sodium hydrogen ion exchanger. And so what it does, though, is it allows us to reabsorb significantly more sodium, right? Sodium that was filtered, more, right? If GFR is higher, then the filtered load of sodium went up too, right? Of everything went up, right? But I mean, sodium's a big one. And so we reabsorb more sodium, right? Here it is being pumped out with our sodium potassium pump. And because of that, remember, if you go back a couple slides, we get increased water reabsorption. So now we're better matched, right? So we don't want, just because GFR went up does not mean we want your urine volume to quadruple for the day, right? If you exercise a lot in one day, your blood pressure elevates during your exercise, which means your GFR could go up. Do you need to excrete more waste just because you're exercising? Nope. Right? And so we want to generate that matching or better matching of GFR to largely tubular reabsorption, right? And that's how it's done, converting the force of the flow rate into a signal, right? Over here where we change the expression of a specific transport protein and enhance our sodium and water reabsorption, right? Because remember, if GFR went up, we were filtering more sodium and water, which means we need to reabsorb more sodium and water. Last but not least, it's kind of cool. This is a micrograph over here on the left where you can see the inside, right? You can see the cuboidal cells of the PCT, right? These big chunky cells. And on the inside, you see these little white strands, right? See these guys? This guy right here, right? And there's one on every cell. It's like one little whisker sticking out, right? That's this primary cilium that's sticking up off of each cell. And it's likely the major transducer, right? Because it's bigger and sticking out into the flow, basically. All right. Now we have this process called pressure diuresis, right? And so if we look at, and so this is an extension of what I was just talking about, right? If GFR goes up, we do want the tubular function to match it. However, if GFR goes up because blood pressure goes up, right? Rising blood pressure increases blood hydrostatic pressure in the glomerulus, increases GFR. It is adaptive to actually excrete a little bit more so that blood volume will fall and blood pressure will fall, right? That's a negative feedback loop. And we'll actually see that in this graph right here, right? Whereas arterial pressure rises, look what happens to urine production, right? This line is like almost vertical, right? So in other words, as you move to the right, right, you get this enormous jump up in urine production. And so let's look at the mechanisms of how that occurs, right? And yes, I know GFR is autoregulated, but it's not perfectly autoregulated, and that's actually adaptive, right? In other words, you don't want GFR to go up by 10%. That's enormous. But having it go up by 1% or 2% might be adaptive in the short term because it helps you regulate your blood pressure, right? And so let's follow this through. I'll change my pen color here. Everything's red. Oop. Okay. So we've got our extracellular fluid volume, obviously adjusted or altered by fluid intake and fluid loss, right? Non-renal fluid loss, but also, and then our renal fluid loss. Here's renal loss, right? Our diuresis effect. And so obviously that's going to adjust our extracellular fluid volume. You've seen this before, which affects our blood volume, right? Blood volume is one portion of extracellular fluid volume, which changes our, you'll see me use the term CVP, central venous pressure, right? That's this circulatory filling pressure of the heart, right? Vascular capacity down here would actually be, you've probably seen the term or heard the term venous compliance. Right? Meaning if the veins are constricted versus not constricted, right? If they're constricted, they have less capacity, which would change their filling pressure. So that also plays into this filling pressure, right? And then of course, that central venous pressure is the driving pressure for venous return, right? And of course, venous return alters EDV. I don't know, not slash. get rid of that, right? But EDV, which alters ESV, right? Which is, that's Starling, right? The Frank-Starling mechanism. And so that's going to adjust cardiac output, right? That's going to play into our blood pressure, our arterial pressure here, right? And of course, total peripheral resistance plays into that too, because we can always write out Poiseuille's law, blood pressure equals cardiac output times total peripheral resistance, right? This is TPR here. All right, here's our cardiac output, right? So we've got all those things playing together to regulate our arterial pressure. And of course, if our arterial pressure rises, we drop that volume, decrease our central venous pressure, decrease our venous return, decrease our EDV, increase our ESV, right? That means more left behind. The heart's contracting less hard, which would decrease our stroke volume and cardiac output, right? And it's going to bring our blood pressure back down to normal. And there is your negative feedback loop for a change in blood pressure that causes pressure diuresis, right? A pressure-induced increase in urine volume, right? That's diuresis. Now, the changes in the mechanotransducer are not the only mechanism of that glomerulotubular balance, and of course, that imperfect glomerulotubular balance leads to the pressure diuresis we just went through. Another mechanism that's important to point out, it probably does play a role, although the mechanotransducer is thought to be sort of like the primary mechanism. Another one, though, has to do with the Starling forces, right? And so here's the inside of the net. Oops, sorry, I have to grab my pen. Right, so the inside of the nephrons over here. Here's the wall, right? So here your PCT, your DCT cells, whichever they are, the tubular cells here. Interstitial fluid, right? ISF, and then your peritubular capillary over here. And remember, your Starling forces are those ones that sort of regulate whether you're reabsorbing or filtering from capillaries, right? So PC is the hydrostatic pressure in those capillaries that would be pushing outward. Pi C is the blood oncotic pressure due to the proteins in here trapped in the bloodstream. Right? So they're going to be pulling water and small solutes inward. And remember, our nephron is doing lots and lots of this, lots of reabsorption, right? But they reabsorb into the interstitium. So you need to get it into the capillary. And so, of course, pi C, right, has to be winning, exclamation point, right? Because that's the reabsorptive force. It does win, right? There are interstitial pressures of both of these, hydrostatic and oncotic, and people argue about what these pressures actually are. But we know for a fact that you get reabsorption. You have to, right? Remember, you have to reabsorb 178 plus liters of the 180 liters per day that you filter. So you know that capillary reabsorption has to be massive and dominant, which means this pi C has to be winning, okay? Now, think about it though. If, let's say that you had increase in blood pressure, all of a sudden there was an increase in blood pressure, what would that do to PC here, right? If you had an increase in blood pressure, right, the incoming blood pressure here goes up, and yeah, it's diminished by the afferent and efferent arterioles, and there'd be regulatory mechanisms and all that kind of stuff. But momentarily, in the short term, that rise in blood pressure would cause this PC to go up, right? If that PC goes up, then you'd think, oh, filtration might occur. Well, filtration probably doesn't occur, but guess what? Reabsorption wins by less, which means things are stuck out here in the interstitial space, right? Including water. And so guess what happens? This pressure rises, right? The interstitial pressure rises because you're just not reabsorbing as effectively. And so guess what? Things are kind of like lingering out here in the interstitium. And yeah, they're going to largely get reabsorbed, but guess what? They have this tendency to leak backwards into the nephron. Call this back leak. So guess what? Your blood pressure went up because your peritubular capillary pressure went up. You reabsorbed less, which increased your back leak. Right? Back leak goes up, which means you're excreting more. Pressure diuresis. Right? It's another mechanism of this pressure diuresis, as well as, and you'd say, oh, glomerular balance, how's it fit into that? Well, when PIF goes up, remember, it's a reabsorptive force here, but it's also causing back leak. So here's your glomerular tubular balance. In other words, you filtered more, right? That would be more over here, right? And because the pressure here rises and would oppose that reabsorption, well, that causes this to go up. So yes, you get diuresis, but how do you get the matching? How do you get better matching of what the nephron's doing, right? Well, how do you avoid this becoming too dramatic? Well, you avoid it becoming too dramatic because this pushes both ways, right? It's not directional. And so this helps oppose that rise in PC that occurred, right? This increase in blood pressure increases this. So now we're reabsorbing, it's helping to reabsorb again too, right? And so it's a little complicated, right? But it's interesting to follow through on this. Let me give you one more example. Let's say you have angiotensin II rise. Blood pressure's low, right? I'm not going to cross all this out, but blood pressure falls, angiotensin II goes up, and you get efferent constriction, right? If you get efferent constriction, you're going to filter more, right? If you filter more, what happens to pi C? Right? If you filter more, you push more volume out, your filtration fraction goes up, right? You're filtering a greater volume. The concentration of the proteins left behind that didn't get filtered goes up, right? If this goes up, that means reabsorption goes up. Aha, check it out, right? So you filtered more, so you're going to reabsorb more, right? If you're, again, the better your peritubular capillaries reabsorb, the more effective your nephron reabsorption can be, because you get less back leak, right? And so filtering more increases, right, our pi C, a reabsorptive force, depending on the pull inward, making us more effective at reabsorbing things that we filtered. Ta-da! Matching what the filtration is doing relative to the tubule, right? We want to have those two kind of go hand in hand. And again, but imperfectly in some cases, like pressure diuresis when it's adaptive, to get rid of a little bit more. Okay. Let's look at the peritubular capillary Starling forces. Just make sure we understand those guys, and then we'll wrap this up, right? And what I'll start with, though, is a review, a reminder. If I can get, it's so hard to grab the pen color here, right? A review of the glomerulus, right? So if you look at glomerular capillaries, here's what's happening. So look at the colors down here. Net hydrostatic is in red. The net oncotic is in blue, right? So I'm going to use the same colors. So in the glomerulus, from inflow end to outflow end, blood, I'll say net hydrostatic pressure, which is largely blood hydrostatic pressure, falls. Okay? Now, let me use the same colors. Go to blue again. If I can get there. Right? Because this pressure is dominant, because the net hydrostatic pressure is dominant, you're filtering. Because you're filtering, you're concentrating your blood proteins. So their concentration is going to rise, right? And so that's your net oncotic pressure. I should have written it down here while I had the red. Right? And this is your net hydrostatic pressure, right? And what that means is you get filtration, filtration, filtration all across the length of the glomerular capillaries, okay? Then you leave the glomerulus, you go through the efferent arteriole, and you enter the peritubular capillaries. Well, look what happens. This pressure keeps coming down, boop, 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 right? And they crisscross, right? The blue one ends up not falling very far from where it already is. And so now the red, note the red now is lower, right, than this blue one. Right? Does that make sense? So the red one now, over here, is lower than the blue one. Well, the net hydrostatic pressure is a filtrative force, and the net oncotic pressure is dominated by pi c, so that's a reabsorptive force. So check it out. So you're going to get reabsorption, 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 reabsorption along the full length of the peritubular capillaries. Right? Hopefully that makes sense. Right? Because it's, again, we're driving our bulk flux based upon which Starling force, which pressure is winning. And in the glomerular capillaries, it's PC, right? Your net hydrostatic pressure is dominated by PC. That's your winner, driving filtration. Whereas when you get over to the peritubular capillaries over here, right, anatomically beyond the glomerulus, hydrostatic pressure has fallen, right? That blood hydrostatic pressure has fallen. It no longer wins. And remember, you concentrated your proteins as you filtered. And so that pressure went up, right? Now it's way up here, nice and high. So it's winning, right? And this guy is dominant, right? Driving reabsorption. And now net hydrostatic pressure always falls, or I should say blood hydrostatic pressure always falls in a blood vessel, period. Any pipe. You run water through it, you run blood through it, whatever, that pressure is going to fall due to friction along the length. But notice the net oncotic pressure rises in our glomerular capillaries because we're concentrating the proteins. And look what it's doing here. It's falling. Why is it falling? It's falling because you're adding volume to the capillaries. Right? As you reabsorb, you're diluting the proteins. And so it is falling. But because they're both falling, right, at a somewhat similar rate, you still maintain that net difference between them. And so you get reabsorption, 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 right? Right? And that, remember, this was up here you had 180 liters per day being filtered. And down here, guess what? You get 178, plus liters per day being reabsorbed, right? That's your filtered load. Here's your reabsorbed volume and load, right? All right. So each capillary set is set up to do exactly what you need it to do. Dramatic filtration, glomerulus, or dramatic reabsorption, peritubular capillaries. Again, for the peritubular capillaries to accommodate what the nephron is doing, right? Lots and lots of reabsorption. Secretion has to go and, it's like salmon swimming upstream. Secretion is going against that bulk flux, which means you need the secreted items to be diffusing out of the capillary. They're not moving by bulk flux, they're diffusing upstream, if you will. Okay. Last thing in this presentation is simply these tables, which would be a good place for you to practice. I'm not going to go through them systematically, but they do lay out our changes in a Starling force. Oops. And one is going up and the other is going down. I thought I had it there. Right, so our change in our Starling force here, right? And then it's saying what would happen to GFR with a given change, right? So if PC goes up, GFR goes up, that should already make lots of sense. What might cause it to go up? High blood pressure, right? Or efferent constriction. And so if you follow through these, though, they should make good sense. Now notice what we have added, though, is the change in peritubular capillary reabsorption, right? And again, we just hit this. If blood hydrostatic pressure goes up, the PC goes up, then look what happens to peritubular capillary reabsorption. It goes down. You know why? Because PC is a filtrative force. If a filtrative force goes down, if a filtrative force goes up here, right, then reabsorption in the peritubular capillaries goes down, right? That should be completely logical. And then what we do is we give you some of the potential causes over here. And again, we just did the example with hypertension. So we have this table. And again, logic here, like practice going through a couple of these and make sure that they make sense. The changes that you see in the Starling forces matching the changes in GFR or peritubular capillary reabsorption. If they make sense, you're good, right? And so we've got two tables showing the increase, and then this one shows the decrease in the exact same Starling forces and their effects. And of course, all the arrows are just the exact opposite direction. The causes will obviously be different. All right, we're going to stop there and continue with another one later.